kids. There's nothing like a nice, refreshing glass of lemonade on a hot, sunny day like today. Oh, lemonade. Let's take a sip. Ah! What kind of lemonade is this?
That's all, friend, the acid. I may have made it a little stronger. Hey, try a little weak base.
Chemical reaction basics.
Before we get into acids and bases, you've got to know some things about chemical reactions.
A chemical reaction happens when one or more substances changes into something else. The written version of a chemical reaction is called a chemical equation.
Writing chemical equations is kind of like writing basic addition problems, but in chemistry we use arrows instead of equal signs. The arrows show that a change is taking place.
The substances on the left of the arrows are called reactants because they're reacting. We add them together with a plain old addition sign. Then comes the arrow. It usually points to the right, but we'll talk more about that in a minute.
On the other side of the arrow, you'll see what's formed when the reactants do their thing. We call them products. The reactants might form one big molecule, or they might form a bunch of smaller molecules. In that case, they have an addition sign between them to show that there are multiple products. Let's try an example.
Here, the reactants are hydrogen or chlorine. So we write down H for hydrogen plus Cl for chlorine. Now, in this case, the reactants just form one product, hydrogen chloride, which we write as HCl.
Now, a reaction where the arrow points to the right is called a forward reaction. But not all reactions move in the same direction.
Say you react hydrogen and chlorine to make hydrogen chloride, like we just did. Then you do something to make the hydrogen chloride separate back into hydrogen and chlorine. We call that a backward reaction, and we draw the arrow pointing to the left.
Hey, are you ready to get really crazy? What if I told you that you could have reactions going in both directions at the same time? In fact, a backwards reaction can't really happen unless a forward reaction happened first, right? So the arrow only faces backwards if there's already a forward one there. We'll get to this another day, but you should know that reactions can go in both directions.
Let's talk about acids and bases.
Definitions of acids and bases.
You might already know a little about acids and bases. In fact, you probably don't have to go far to find either one. Your own kitchen probably has acids in it, like lemon juice and vinegar. And hey, your own blood is a base.
But what are acids and bases?
You probably know them by their properties, like how they taste and how they feel.
Acids usually taste sour, so they're in lots of foods like lemon juice and sour candy. Some acids aren't for eating, though. They can hurt you if they're strong enough. Some criminals have even used acids to erase their own fingerprints.
On the other hand, bases usually feel kind of slippery and they tend to have a bitter taste. Lots of soaps have bases in them, but don't let that fool you. Strong bases can be just as dangerous as strong acids. And that, my friends, is why we don't take baths in drain cleaner.
No, it's still bad. Ah!
When it comes to nailing down exactly what makes acids and bases do their thing, though, scientists have pretty much agreed on a set of 3 definitions. All of them are actually right. They just work a little differently. We're going to talk about all 3 of them, so get comfy.
Hey, ladies and gentlemen, I'm Dink Michaels, and welcome to Chem Center's coverage of acids and bases. Here to talk about what makes a really great acid or base, we have Swedish scientist Svante Arrhenius. This guy was really one of the pioneers of acids and bases. In fact, one of the first definitions of acids and bases is called the Arrhenius definition. Artie, welcome. Tell us about your theory.
Sadinka, so good to be here. You see, an acid is anything that adds hydrogen ions to a water solution. A base is anything that adds ions made of hydrogen and oxygen.
I'm going to need you to explain that again, Artie.
Say we add some hydrogen chloride to water, so all the hydrogen and chlorine ions separate. Now there's extra hydrogen in the water, and since it came from the hydrogen chloride, we know hydrogen chloride is an acid.
Yeah, and is it true that a hydrogen ion is just a proton with no electrons?
It is, Dinka. But hydrogen usually doesn't last long by itself in solutions. It gets lonely and bonds with water to form an acid molecule called hydronium. That's 3 hydrogens and 1 oxygen, or H3O. Now, I like to talk about plain hydrogen because it's simpler, but hydrogen in an acid usually means hydronium.
So that's the acid side of things. Gummy Bear.
Ooh, don't mind if I do.
Now, tell us about bases and that hydroxide ion that makes them so special.
Well, Adinka, hydroxide molecules are made of a hydrogen atom and an oxygen atom, and they're the foundation of all bases. Let's go to the taper. Instead of hydrochloric acid, let's see what happens if we add sodium hydroxide to water. Sodium hydroxide is a base made of sodium and hydroxide, and it breaks apart into sodium ions and hydroxide ions. All that hydroxide flooding into the solution means sodium hydroxide is a base.
If sodium hydroxide breaks into sodium and hydroxide, why doesn't hydroxide ion break up into hydrogen and oxygen?
That's a talking gummy bear. Hydroxide is covalently bonded, so those guys are stuck together for good. When the ionic bonds in sodium hydroxide fall apart, the hydroxide stays in one piece. That's why bases depend on them in the clutch.
That's some great commentary from a true legend. Thanks, Artie. Now, 20 years after that guy, a couple of young bucks named Johannes Bronsted and Thomas Martin Lowry changed things up. They said that Arrhenius wasn't exactly wrong, but he didn't cover everything. Looks like we've got them by satellite. Let's patch them in, Bob. Hey guys, how you doing?
Great, Dink. You know, it's tough to change up the words of a legend, but good old Lowry and I were pretty sure that an acid is a molecule that can donate a proton. Then we defined a base as a molecule that can receive a proton. And I think the game was changed forever.
Wait! If an element gains or loses a proton, doesn't it become a totally different element?
Normally it would, but in this case, the proton they're talking about is actually a hydrogen atom that ditched its 1 electron. It can bond with other atoms to make a new molecule, but it can't just join the nucleus of another atom.
So adding a single proton just means adding a hydrogen atom that's lost its electron, which sounds an awful lot like what Arrhenius said about acids, doesn't it? Let's see how it works.
Let's go back to our old example of adding hydrochloric acid to water. Remember that HCl splits into hydrogen and chlorine. But the hydrogen's really reactive, so it attaches to water to make hydronium. The chlorine doesn't have anything to bond with, so it just hangs out by itself.
Hydrochloric acid gave up a hydrogen proton, and water picked it up. Scientists would say that hydrochloric acid donated the proton, so it's an acid. Water accepted it, so it's a base in this reaction.
You heard it here first, chemistry fans. So Bronsted and Lowry didn't really say Arrhenius was wrong. Hydrochloric acid still added hydrogen to the water, but in this case, the water swooped in and took the hydrogen, and that was all Bronsted and Lowry. They say that acids and bases always come in pairs. An acid can't donate a proton if there isn't a base to receive it, and a base can't receive something that an acid didn't donate. You know what I mean?
There's another way to look at this. According to Bronsted and Lowry, nothing is an acid or a base until it reacts with something. Once it's donated or accepted a proton in a reaction, then we can decide what it is.
Hey, we're 2 definitions down and 1 to go. The last definition scientists use is called the Lewis definition. It really shook people up because, get this, it doesn't even mention hydrogen and hydroxide.
Whoa. Okay, are you ready? According to Lewis, an acid is any substance that accepts an electron pair. A base is anything that donates an electron pair.
What?
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 Dude, calm down. It's not that bad.
Lewis isn't actually that far off from Bronsted-Lowry. It just looks at things in a different way. See, we've been trading hydrogen ions all over the place, but we haven't really talked about how they bond. In fact, hydrogen ions don't have any electrons. So how can they form bonds in the first place?
It's all about a special kind of bond called a coordinate bond. A coordinate bond is a bond where both electrons come from the same atom.
See, our hydrogen ion has a positive charge, and it's super attracted to any lone pairs nearby. They're just so negative. As soon as it gets close, zip, it sticks like Velcro, no electrons needed. Coordinate bonds are a type of covalent bond because the lone pair lives in the space between the 2 atoms.
The coordinate bond is the key to the Lewis definition. A Lewis base is anything that uses a lone pair to bond with something else. The other particle is a Lewis acid because it sticks to the lone pair. Another way to put this is that a Lewis acid is an electron pair acceptor and Lewis bases are electron pair donors. Now let's check to see how it works with actual molecules.
When oxygen bonds with hydrogen to make hydroxide, or OH, it still has 3 lone pairs, perfect for attracting hydrogen ions.
Now, Bronsted and Lowry said hydroxide is a base because it accepts the hydrogen ion. The base could be anything with a lone pair. In fact, it could be anything with empty orbitals. If it can stick to the lone pair, it's a Lewis acid.
Like we said, the Lewis definition really shook things up in the science world. Lewis didn't contradict the earlier definitions, but the definition of acid and base suddenly included all kinds of things that weren't included before. Crazy!
Don't worry. The more chemistry you do, the more comfortable you'll get with these definitions. Just remember, the 3 definitions of acids and bases all kind of say the same thing, just in different ways.
Hey, great job! Who knew you'd be an expert on acids and bases so soon? Of course, now that we know what makes them, we should probably figure out how they behave.
Properties of acids and bases.
Now we know exactly what makes acids and bases, but there's more stuff you should probably know about them.
For one thing, it may seem like acids and bases are opposites, but sometimes they're just a proton apart.
You learned from Bronsted-Lowry that acids and bases come in pairs, right? Well, a few special pairs called conjugate pairs can trade identities just by passing a single proton back and forth.
I'm base. No, I'm base.
Hydronium and water make up one famous conjugate pair. Notice that hydronium, or H3O, has exactly one more hydrogen ion than good old H2O. Interesting.
Now, if one of the hydrogens from hydronium breaks off and joins up with the water molecule, everything changes. Up is down, black is white. The acid hydronium is now just plain water, and the old water molecule becomes a fancy new hydronium.
Hey, it's cool. They can switch back. All they have to do is pass that hydrogen ion back. Now we have just what we started with.
Water also forms a conjugate pair with hydroxide. Hydroxide is a base, which makes water an acid in this experiment. But if one of water's hydrogen ions breaks off and bonds to the hydroxide, what happens? Water becomes hydroxide, and hydroxide becomes water. It's madness!
You might have noticed the pattern formed by conjugate pairs. They're always different by 1 proton. That's why they switch identities so easily. You should also remember that they're always 1 acid and 1 base. They might switch back and forth, but they're always one of each.
Now, you've probably noticed that not all acids and bases act the same way. Some are safe to put into our bodies, and a few are even important to make our bodies function. On the other hand, some could eat the fingerprints right off your fingers. The difference is the strength of the acid or base.
The strength of an acid or base depends on how completely it dissolves in water. The more it dissolves, the stronger the solution.
When a molecule falls apart and gets dispersed through the water, it frees up lots of hydrogen or hydroxide ions to work their magic. That's called a strong acid or base. Molecules that stick together better don't add as many ions to the solution, so they make a weaker acid or base.
Warning! When it comes to acid and bases, strength is not the same as concentration. Strength tells us how completely the molecules separate in water. Concentration tells us how many of the molecules there are in the solution. Don't get confused.
Now there's one strong acid you carry around with you all the time. The acid in your stomach has to be strong enough to break down the food you eat, so it's pretty strong stuff. So why doesn't it eat through your stomach and spill all over the place?
That's a great question. Stomach acid stays put because the lining of the stomach is a thick layer of mucus mixed with a base called bicarbonate. If the acid tries to escape, the bicarbonate turns it into water.
Good old mucous membrane. My mummy used to say, a running nose is a waste of good insulation.
So how do you know whether an acid or base is safe to work with? Best to test before you come into contact with it. The strength of an acid or base is measured using a scale called the pH scale.
The pH scale starts at 0 and ends at 14. Acids are on the lower end between 0 and 6. Bases take up the higher end between 8 and 14. The ends of the scale mean stronger substances, so if you get something with a pH of 1 or 13.5, watch out. If you're working with something closer to the middle of the scale, you probably don't have too much to worry about.
In fact, anything with a pH of 7 is neutral. It isn't an acid or a base. Pure water has a pH of 7.
Nobody really knows what pH stands for, because it's a very old label. We do know it basically measures how many hydrogen ions there are in a solution. The lower the pH, the more hydrogen ions you'll find. That's why a pH of 0 is a strong acid packed with hydrogen.
Scientists use a special equation to find the pH of a solution. You won't always need to find the pH yourself, but it's a good skill to have up your sleeve. Let's try it.
The equation for finding pH is pH equals negative log H. This looks like some serious math, right? Well, the good news is that all you need to solve it is a scientific calculator and the molarity of the solution.
You remember our friend molarity, right? It's the number of moles of solute in a given volume of solution. We write it as moles over liters, or M.
So the log in this equation stands for logarithm. That's a math term that means the exponent that a base number needs to be raised to if you want to get a certain number. For example, the logarithm of 1,000 is 3, because 1,000 is based on the number 10, and raising 10 to the third power is what gets you 1,000.
You don't need to know the details of logarithms to find pH, though. As long as you know where to find the log button on your calculator, you're good.
Anyway, we're looking for a negative logarithm, so press the negative button first. Then press log. Then enter the molarity of the solution and press the equal sign. And there you go. Your answer is the pH of the solution.
Sometimes, scientists don't need to calculate pH using math. They just need to test what's in front of them. To find the pH of a solution without math, they use handy things called indicators. Indicators change color to announce pH to the world. There's a color for each pH number, so it's easy to tell what you're working with.
Some indicators are liquids that change color when they're added to a solution. In fact, one natural indicator is the juice of the red cabbage. It's naturally sort of pinkish, but it turns red in acid solutions and green in basic ones. Neutral solutions make it stay its regular cabbagey pink.
Not all indicators use the same colors, so make sure you know which indicator and color system you're using. You can check with your teacher if you're not sure.
Hey! I thought water had a neutral pH. But you said earlier that it's an acid, and then you said it was a base. So which is it? Is water an acid or a base?
Actually, it's neither, or both.
But what does that mean?
Some substances can act as either an acid or a base, depending on the situation. We call those substances amphoteric.
Amphoteric molecules are like shapeshifters. They act like an acid when there's a base around, and like a base when there's an acid around. That means they can either donate or accept a proton from another molecule. Base!
Water is the most common amphoteric substance on Earth. It can donate a proton to become hydroxide or accept a proton to become hydronium. That's why it forms conjugate pairs with both hydronium and hydroxide.
So water is amphoteric and it has a pH of 7. That's a neutral pH. So do amphoteric molecules always have neutral pHs?
Nope. Amphoteric molecules can be pretty strong acids or bases. The bicarbonate in your stomach's lining is a good example. As a base, it has a pH of 3.7, but it can also be an acid with a pH of 10.3. That's not neutral at all.
Hey, cool! Now you know about some of the properties of acids and bases. Now comes the real magic.
Magic!
What happens when you mix them together?
Acid-base reactions.
Acids and bases help us out all the time, but sometimes they can be... sorry. I meant, excuse me. I meant to say, it can be a little intense. Sorry. I had chili for lunch, and that stuff is deadly, if you know what I mean.
Sound familiar? Some acids in your own body can get out of hand, like when stomach acid gets all riled up and finds its way into the esophagus. That's called heartburn, and Americans spend more than $10 billion a year on medication to get rid of it.
So how do we get those rogue acids or bases under control? There has to be a better way.
You're in luck. There are a couple of ways to limit the effects of acids and bases.
The first way is to just add water. Diluting an acid or base with something neutral, like water, means there are fewer ions of hydronium or hydroxide in a larger amount of solution.
That's why science labs have eye washes. If you get something acidic or basic in your eyes, water does a pretty good job of diluting whatever's in there.
Another way to keep acids and bases in check is to neutralize them. That means to equalize the number of hydrogen and hydroxide ions so neither one is in charge.
And how do we make them equal? Well, it depends. If you have too much acid, add a base. If you have too much base, add an acid.
A reaction between an acid and a base is called a neutralization reaction. Let's see how it works.
Let's start with some hydrochloric acid, good old HCl. We want to neutralize it, so we add a base called potassium hydroxide. That's KOH.
The hydrogen from hydrochloric acid team up with the hydroxide in the potassium hydroxide. That's 2 hydrogens and 1 oxygen, which makes water. The leftover reactants are potassium and chlorine, which pair up to make a salt called potassium chloride.
That's pretty much how all neutralization reactions go. A mixture of acid and base produces water and some kind of salt. Water is neutral, remember? So it makes sense that it's the product of a neutralization reaction.
Now, a neutralization reaction doesn't always produce a solution with a perfect pH of 7. A strong acid or base has so many ions of hydrogen or hydroxide that mixing it with something weaker might not neutralize them all the way. But it will be more neutral than it was before.
Sometimes, scientists need a solution with a pH that won't change, even if they add extra acid or base. When that happens, they make a buffer solution.
A buffer solution is made of a weak acid or base mixed with its conjugate pair. So there's a little acid and a little base in there. The mixture acts like a sponge, neutralizing any extra hydrogen or hydroxide ions. That keeps the pH from changing too much.
The buffer won't keep the pH stable if it's totally flooded with a ton of really strong acid or base, but it does help keep the pH stable through quick shots of anything that might change it right away.
Buffer solutions are useful for lots of reasons, but one is really important.
Blood!
Actually, yeah. Blood is slightly basic, and your body needs it to stay that way. It's a buffer solution, so it stays at about the same pH, even if a little acid or extra base gets into it. Cool, huh?
All this neutralizing and buffering action is what happens when you use acids and bases to keep each other in line. But there's another way that acids and bases can interact. It's called a coordination complex.
Coordination complexes are molecules formed when a bunch of non-metal atoms bond to a central metal atom or ion using a coordinate bond.
You remember coordinate bonds, right? They're what happens when an atom or ion sticks to a lone pair on another atom.
In this case, the metal atoms in the middle have blank spaces in their outer orbitals. They're perfect for bonding with the lone pairs on passing nonmetals.
The nonmetals that surround the inner metal atom are called ligands. They bond around the metal atom like skydivers in a ring. Scientists keep track of the number of ligands that bond with the atom in the middle because it tells them how the molecule might be shaped. The number of ligands is called the coordination number. It can range from 1 to about 12, but the most common coordination numbers are 2, 4, and 6.
So what do coordination complexes have to do with acids and bases? Well, according to that crazy Lewis definition, they only form when Lewis bases bond with a central Lewis acid.
The metal atom is a Lewis acid because it accepts electron pairs from the other atoms. The nonmetal atoms are Lewis bases because they donate electron pairs. If the coordination complex has an electrical charge, it's called a complex ion. Otherwise, you can just call it a coordination complex.
So coordination complexes are made when a Lewis acid accepts lone pairs from a bunch of Lewis bases. But why are they important?
Well, there are a lot of scientific uses for coordination complexes, but a super important one is flowing through your veins as we speak.
Blood?
Hemoglobin is a part of your blood, and it's a coordination complex. Oxygen molecules become ligands and bind themselves to the hemoglobin, then hitch a ride to wherever they need to go. Coordination complexes make sure every part of your body gets the oxygen it needs.
Other mixtures.
Not all mixtures are solutions. Remember, the particles in a solution dissolve, but there are lots of mixtures that don't dissolve when you mix them. They're called colloids and suspensions.
A colloid is made of tiny particles spread out evenly in another substance. The particles are so tiny they don't even show up under a microscope.
The particles in a colloid can be either solid or liquid, and they can hang out in a solid, a liquid, or a gas. Basically, the only combination that can't be a colloid are gas particles mixed into a solid or liquid.
A few examples of colloids are milk, hairspray, smoke, gelatin, cheese, and quicksand.
Suspensions are a little different from colloids. The particles in a suspension are like the snow in a snow globe, which eventually drifts to the bottom of the container. Suspensions are made of bigger particles and they don't stay suspended forever.
Some examples of suspensions are fog, paint, and muddy water, all of which will separate if you leave them alone.
Hey, now you know all about acid and base solutions and other kinds of mixtures.
So, go forth and mix, my friends.